Hey there. In this video, we are going to solve a differential equation using a substitution. Now, the first thing I want to do is get this into a different form where I have a 0 on the right side of the equation. And this is going to help me to kind of organize this so that I can hopefully prove that the coefficients for my differentials dy and dx are homogeneous. Okay, so the first thing I'm going to do is subtract over everything that's on the right side. So I'm going to have negative, actually here, we'll put the x first. So we'll have x cubed minus y cubed plus xy squared dy dx equals 0. So now it's homogeneous in the sense that I have a 0 on the right side of the equation. I want to see if these coefficients are homogeneous as well. And just to make it look really standard as to what we do with most of these, I'm going to multiply through by dx as well. And then it should look familiar, similar, or the same as how we write a exact equation. So I have x cubed minus y cubed times dx plus xy squared times dy equals 0. And so I want to try and use a substitution for when the coefficients on the dy and the dx are homogeneous. So I'm going to just double check to make sure that that's actually the case here before I commit to that method. So this first coefficient here, x cubed minus y cubed, would be m of xy. And then the xy squared that's multiplying by dy would be n of xy. I'm choosing this the same way I would for an exact equation. What's multiplying by dx is your m, and what's multiplying by the dy is the n. Now, to check and see if this is actually, each of those are homogeneous, I'm going to replace x and y in these functions with tx and ty. So I want to find m of tx and ty, and I want to see if I simplify this, I can factor out a power of t, and in fact, factor all of the t's out. So I'm replacing x and y with tx and ty. So for this first one, that's going to be tx cubed minus ty cubed. And I can distribute that to be t cubed, x cubed, and t cubed y cubed, which allows me to factor a t cubed out of everything. So I get t cubed times the quantity x cubed minus y cubed. So in fact, now I was able to pull out all the t's, and I just have t to the third power times the original function m. So this is a homogeneous equation of degree 3, since I was able to pull out a power of 3 for the t. Now, in order for the substitution to work, I have to do the same thing for n, and I need to be able to pull out the same power of t everywhere. So n of tx ty would be tx times ty squared. And so I do have a t cubed in there that I can factor out to give me t cubed times xy squared. So both of these are homogeneous, and they're both degree 3. So I'm going to be able to use a substitution. Now I just have to decide which substitution to use. Now, you're usually looking at, well, which is the more complicated? And here the n is the simpler of the two coefficients. And so if it's simpler, I want that one to be multiplying by the more complicated differential. And so what I'm going to choose is the substitution. I'm going to let y equal ux. And then that means that dy is going to be equal to u dx plus x du, just using the product rule there to find the derivative of this equation, y equals ux. Okay, so since n was more simple than m, I want to have the more complicated dy there. So I'm going to go ahead and do the substitution. When I'm done, I should have no more y's anywhere in the equation. Everything should be replaced with just u's and x's. Okay, so I have x cubed minus y cubed, so that's going to become minus ux cubed. dx plus x times ux squared times dy, which is the u dx plus x du. And all that is still equal to 0. Okay, so everything with a y has been replaced with u's and x's. And I just need to do some cleanup here. And you should get some cancellation going on or some combining of like terms after you've distributed this out. So I'm going to distribute out everything completely. This will give me x cubed dx minus u cubed x cubed dx plus x squared, u squared x cubed. And let's all distribute all of that at once here. So this will give me, I'm going to have a u squared and a u, so that's going to be u cubed times x cubed dx. And then distributing everything to the second term, the x du, that is going to be u squared x to the fourth du, all equals 0. And as I was hoping, I do have some cancellation here. I have a negative u cubed x cubed dx and a positive u cubed x cubed dx. So those cancel out, and I end up with a much simpler equation, x cubed dx plus u squared x to the fourth du equals 0. Okay, at this point, you have a choice of how you want to solve this. For most of them, it will be a separable equation, and you would also be able to use an integrating factor. So you kind of just pick the one that you find your favorite to use. I'm going to go ahead and use separation of variables here, but you could probably do an integrating factor as well if you wanted to try that out. Okay, so I'm going to split this up. I'm going to keep the u's on the left side since those are related to my y, and that is my independent variable that I ultimately want to solve for. So I'm going to leave the du on the left side and move all the x's over. So that's going to be u squared x to the fourth du equals negative x cubed dx. And then I need to divide by x to the fourth to separate the variables. So I end up with u squared du equals negative dx over x if I divide by x to the fourth. And now the variables have been separated, and I can go ahead and integrate both sides of this equation. So u squared is going to be 1/3 u cubed. And I'll throw the constant of integration on the right side for both integrals. And then I get negative the natural log of the absolute value of x plus c1 on the right side. Okay, now how much you solve this is kind of up to you. Unless the instructions are really explicit on the form of the final answer, I am going to go ahead and solve this all the way for y. And I do want to actually note that the instructions on this problem said that x is greater than 0. So I'm going to actually be able to drop off the absolute value on the x inside the natural log there. Okay, so next I'm going to get rid of the 1/3. I'm going to multiply by 3. So u cubed is equal to negative 3 natural log of x plus, and I'm going to just fold that 3 when I multiply it by c1 into a new constant, and I'll call that c2. And then at this point, I'm going to go ahead and cube root. So u is equal to negative 3 natural log of x plus c2. And I'm going to go ahead and use an exponent for that. You can use a cube root or a 1/3 power. Either is fine. And now it's time to remember what our original substitution was. y was equal to ux, which means that u is equal to y over x. So I can replace u with y over x here. So y over x equals negative 3 natural log of x plus c2 all to the 1/3 power. And I can multiply by x. So y equals x times the quantity negative 3 natural log of x plus c2 to the 1/3. Now, if you did this in a different order, for instance, I could have reversed the u substitution a little bit earlier. The form of your answer might look slightly different, but it should be equivalent to this.